Okay, I'm going to go ahead and lecture here on the basics of the electric force. Make sure that you watch the two demonstration videos, however, prior to this lecture. That is charging by friction and also charging by induction. Follow the directions for uploading your notes to Schoology. Each section of notes, it will be an individual assignment, and it is worth 5 points. Okay, so the electric force. Electric force is caused by a basic property of matter that we refer to as electric charge. Electric charge is just simply the name that is given to this property of matter that gives rise to the electric force. Okay, first of all, there are two types of charges. There's first of all positive charge. Positive charge is associated with protons, which in part make up atomic nuclei. There is negative charge. Negative charge is associated with electrons, which are also some of the basic constituents of matter, the basic constituents of atoms. Okay, now in my two demonstrations, charging by friction and charging by induction, basically what you were seeing was, first of all, the transfer of electrons from one object to another, or secondly, the flow of electrons within an object, that is a conducting metal, for example. Okay, and then the electric force itself manifests itself two different ways. That is, first of all, there's a force of electrostatic repulsion, that is, like charges repel, and a force of electrostatic attraction. That's where you have opposite charges attract. So, like charges repel, and opposite charges attract. Okay, now the basics of the electric force was first of all figured out in the late 18th century, and it turns out that this is actually well before our understanding of the atomic nature of matter, well before we knew anything at all about positively charged protons, for example, in atomic nuclei, and negatively charged electrons within atoms themselves. So then, therefore, how do you then describe the electric force if you know nothing at all about the nature of atomic matter? Well, let's go to the late 18th century. So we're talking about the late 1700s. Okay, and we actually get to Benjamin Franklin. Okay, Benjamin Franklin today is kind of remembered as one of the founding fathers of the nation. And then kind of like on the side, he dabbled in science and entrepreneurship and so on. It's actually backwards. For most of his life, he was a serious scientist. He actually had a PhD in physics, and he was an expert in Newtonian gravitation. And it's only later on in life that he kind of dabbled in government and became one of the founding fathers of the nation. So we tend to picture Benjamin Franklin a little bit backwards for that reason. Okay, now here's how Benjamin Franklin investigated the electric force. Franklin envisioned the electric force as being caused by a fluid. And this fluid can flow from one object to another, or could flow within certain types of objects, such as conductors. This fluid can flow from one object to another, or flow within certain objects, such as conductors, and he refers to this electric fluid as electric charge. So notice that he actually gets the basic idea here correct with this assumption. We now know today, for example, with the process of charging by friction, that electrons are basically torn out of one object, if you will, and then transferred to a second object. Or in the case of conducting materials such as metals, you can easily have the flow of electrons within the metal itself. So Franklin gets the basic idea correct, but of course this is well before our understanding of the atomic nature of matter. He coins the phrase electric charge to describe this fluid, and we still use it today. Here's how Franklin envisioned a positive charge. He pictured an object that is being positively charged as having an excess of this fluid, and an object that is negatively charged as missing some of this fluid. We still use these terms today, but now we reference them in terms of positively charged protons, for example, and negatively charged electrons. The reason why, by the way, you don't see the electric force around you, except for under the circumstances in my demonstration video, is that for the most part, matter around you is neutrally charged. That is, it has an equal amount of protons and an equal amount of electrons, which then all cancel each other out. It's only under the circumstances that you saw in my demonstration videos, for example, that you can easily see the manifestations of the electric force itself. So Franklin gets the basic idea correct. Once again, this is well before our understanding of the atomic nature of matter. So positively charged is an object with an excess of this fluid, and negatively charged is an object missing some of this fluid. And we still use these terms today. Okay, now even as far as Franklin got in his investigations of the electric force, he actually wasn't the person who came up with a mathematical description of the electric force. That was a Frenchman who lived around the same time. This man's name was Charles Augustin de Coulomb. Here's how you spell his name, and the mathematical description of the electric force is referred to as Coulombs Law. Mathematical description of the electric force. Coulomb used a pendulum apparatus, much like the pendulum apparatus that I was using to demonstrate the process of charging by friction. He used that pendulum type of demonstration as an experiment to quantify mathematically a description of the electric force. Here's the basic description of the electric force itself. Mathematically, it behaves in a very similar manner to Newtonian gravitation. So for example, let's say that I now have two charges. The letter that we always use to refer to electric charge is the letter Q. Here's a charge Q1 and a charge Q2. Charge is considered to be a fundamental property of matter, and the metric SI units of charge are referred to as coulombs. Which we usually abbreviate simply as C. So let's say I have two charges here, Q1 and Q2. And they're separated here by some distance. This distance here is equal to R. Now, like the force of gravity, the magnitude of the electric force obeys an inverse square law. That is, the force that occurs between the two charges is inversely proportional to the square of the distance. So for example, if you take two charges and you double the distance between them, then therefore the magnitude of the force is 1 over 2 squared, or 1/4 of its original value. If you triple the distance between the two charges, then the magnitude of the electric force is 1 over 3 squared, or 1/9 of its original value, and so on. So like in the previous unit, when describing the intensity of sound waves, which also obeyed an inverse square law, like the force of gravitation, the electric force obeys an inverse square law as well. The ultimate reason for this is because we live in a three-dimensional universe. Okay, the magnitude of the electric force that occurs between the two charges is also proportional to the product of the charges themselves. So then therefore, the force is proportional to the product of the two charges. So if you increase the value of one of the charges, this then increases the value of the electric force that occurs between the two charges. Okay, combine these two proportionalities together here into one expression. So the electric force is proportional to the product of the charges divided by the distance squared. Okay, compare this to Newtonian gravitation from the first semester. Okay, if you recall from the first semester, if you have two masses, M1 and M2, that are some distance apart from each other, R, the magnitude of the gravitational force is proportional to the product of the masses divided by the distance squared. Same sort of relationship here for Coulombs law. Okay, if you also recall from Newtonian gravitation, there was a fundamental constant that basically turned this proportionality into an equal sign. That fundamental constant, remember, is referred to as capital G and is called the universal gravitational constant. Like so. Okay, there is an additional fundamental constant that is present within Coulombs law as well, that once again turns this proportionality here into an equal sign. This is a fundamental constant, much like the universal gravitational constant. It's basically one of nature's fundamental numbers, and it describes the magnitude of the electric force that occurs between two charges. Okay, the number itself is usually just written as small k. The value of small k is extremely large. It's large compared to the value of capital G. Recall that the value of capital G is quite small, 6.67 Newton meters squared per kilogram squared, while the value of capital K is literally 9 billion. It is 9 times 10 to the 9th Newton meters squared per Coulomb squared. Here's where the units, by the way, of this constant come from. They come from this fundamental description. So we have force in terms of newtons, and then down here is meters squared, which we then move up to the numerator on the left-hand side of the expression. And then right here is coulombs squared, which we then move down to the denominator on the left-hand side of the expression, thereby getting the units of K all by itself. So you have Newton meters squared per Coulomb squared, like so, as the units of small k. So compare small k here, that number, compared to, for example, 6.67 times 10 to the minus 11, I meant to write, by the way. Compare that to capital G, the universal gravitational constant, which is obviously a lot smaller. This means that, fundamentally speaking, the electric force is much bigger than the force of gravity. We still today, here in the 21st century, don't exactly understand why that is. Why is gravity so weak, for example, compared to, say, the electric force? Okay, I'm going to go ahead and pause the film here. This is part 1 of today's lecture. I'll go ahead and take a look at part 2 in just a few moments.